Alright, going to do 7.5 part 2, just some more of using this Laplace operator to solve differential equations. We're going to do kind of a cheap example here real quick, just because this may be something that shows up in your homework. Sometimes you may have to shift your equations over to be able to solve them. So a quick example of when you need to do that. Let's say we have w double prime of t minus 2 w prime of t plus 5 wt is equal to negative 8 e to the pi minus t. With initial conditions, w of pi is equal to 2, w prime of pi is equal to 12. Okay, the Laplace method only works if your initial starting point is at 0. And that comes from the definition of what happens when you have the derivative inside the Laplace operator. So because we have these pi's here, we may have to shift. So to shift our function, we need t to start at 0. Right now it's starting at pi. So to do that, we're just going to let some other function y of t equal to w of t plus pi. Alright, so that way anytime I plug in 0 for t into y, it's the same thing as plugging pi into w. This is going to change a lot of our equation around though, so we just have to be a little bit careful. So what I would do is I would just take the equation that we started with, and let's just replace all of the t's with t plus pi's instead. So w double prime of t plus pi minus 2w prime of t plus pi plus 5 w of t plus pi. And that's going to be equal to, just be a little bit careful about this right hand side, so negative 8e. If I plug in t to be t plus pi, that negative sign is going to distribute, and then the pi's are going to cancel. This is just going to be e to the negative t. Okay, your initial conditions are also going to shift. So again, if I plug in, if I'm moving everything and shifting everything by t plus pi, that's going to move the initial conditions backwards. Because now, for y, not w, for my y values, I want my t to be 0, because plugging 0 in for the y is the same thing as plugging pi in for the w. So y at 0 is going to be 2, and then y prime at 0 is going to be 12. Okay, we don't have to do this example because it's actually the same example we just did in the last video. I just wanted to show you that sometimes you may need to shift to be able to use the Laplace operator. All right, so now let's do an actual example. So far, we have only looked at examples that could have been solved using other methods. This time, let's look at an example that only the Laplace operator can solve for us. So something like this. Okay, so y double prime plus 2t y prime minus 4y is equal to 1, with initial conditions y of 0 is 0, and then y prime of 0 is 0. So we could not solve this one before because of this t right here. We only had 2 different kinds of second order differential equations we could have solved. Ones with constant numbers out in front, and then we also had that equidimensional case where the t squared and then a t term was out in front of the double derivative and then the single derivative. This is kind of the in-between. We do not have a way of solving this. Okay, except now that we've learned the Laplace operator. So we're going to take the Laplace transform of both sides. And we'll just kind of, to write it all out at this point. So we're going to do the Laplace of y double prime plus 2. We have to be a little bit careful here because that t is a part of the variable for the Laplace operator. It does have to stay on the inside. That is not a constant. So the Laplace of t y prime, and then minus 4, the Laplace of y. And that's going to be equal to the Laplace operator of 1. We'll just write it out, but I hope it's pretty obvious what that's going to come out to be. That's something that we did before, if you remember. So that it's also on that table that we have. So now for the derivatives. I'll make separate lines here for these derivatives because it's just a formula to them. Whoops, sorry. So we're going to do the Laplace operator of the second derivative, and then just from the formula, remember this is s squared, the Laplace of the original function minus s times the original function at 0 minus the derivative at 0. Okay, so again, there's just a formula to that. Plugging in our initial conditions, y of 0, remember, is 0. The first derivative at 0 is also 0, so both of these terms just disappear. My second derivative is just s squared and then the Laplace of y. Okay, we also have to do the first derivative. This one's going to be pretty similar. So the Laplace operator of the first derivative. Oh no, sorry, we don't want just the first derivative, right? We have t times the first derivative that we need to find the Laplace operator for. Okay, so for this one, again, it's a formula attached to it. Remember when you multiply by a t onto something, that means to take the derivative. If it was a t squared, it would be the second derivative, t cubed, the third derivative. So again, a couple of videos back, there was a formula for when you multiply by a t onto a function that you're doing the Laplace operator for. This is going to be the derivative with respect to s of the Laplace operator of y prime. Again, so that's just kind of writing out what that t is doing. Also remember that it alternates positive and negative depending if it's odd or even powers. If this was a squared, it would be a positive second derivative. If this was cubed, a negative third derivative, and so on and so forth. But now that we have that, now we can kind of write out what this is going to be. So this is going to be the negative derivative with respect to s of the Laplace operator of y prime. The Laplace operator of y prime, there was a formula for, that's s, the Laplace operator of y, and then minus just the function at 0. All right, and again, so just the formula for that one. Just to clean this up a little bit, because the Laplace, but the function at 0, remember, is 0. This is going to be negative, so we're going to have to do a product rule here, because don't forget that the Laplace operator has s's embedded into it. So there's s, and then this also has s's, so when we take the derivative, it's going to be first s, and then the derivative of the second, so we'll just, let's see if I can clean that up, of the Laplace operator. Okay, and then that's going to be minus, because of this negative on the outside, the second derivative of the first, but the derivative of the first is just 1, so here we're just going to get the normal Laplace operator of y. And there's not really too much that you could do here. I know in the books they like to write out this L as a capital Y. So I might start doing that just to kind of save some time here. So we can write it like this. So anytime you see a capital Y, we're referring to the Laplace operator of y. So negative s, the first derivative of the Laplace transform, minus the Laplace transform. Okay, cool. And now that we have these things, we can plug that back into this first equation here. So the first thing is that second derivative, which was just s squared, and then Laplace of y, so capital Y of s. And then we got to be careful, right? Because there's a plus 2, and that plus 2 needs to distribute into the Laplace of ty prime. So we're just going to multiply by 2 onto these two terms. So negative 2s y prime of s, and then minus 2 times just y of s. And that's going to be also the last term, negative 4 times just y of s, and that's equal to, again, this is coming from the table of the book, the Laplace operator of 1, it's just 1 over s. Okay, cleaning this up a little bit, we have a bunch of stuff that we can combine together. We have the derivative, and then we also have just the function itself. So I'll leave the derivative one out front, so negative 2s y prime of s. And then the other ones will combine together. So we have an s squared The -2 and the -4 combine to be a -6, and that's just on the Laplace operator y of s. This, unfortunately, we're going to have to solve using differential equations because we have a derivative here. But we can do it because this is just a first-order linear differential equation. This goes back to chapter 2 stuff, chapter 3 stuff. I can't remember exactly where it was. But remember, this is that P, Q, and then the integrating factor kind of a setup. You have to have the coefficient on the derivative be 1. So we're going to divide everything by -2s. We're going to get the y prime out in front. This will be a minus now. So when I divide this thing by 2s, I'm just going to divide each of the terms by the 2s. We're going to get s over 2, and then minus, that's going to be 3 over s. Just double checking to make sure I got it right. That looks good. So that's just times the function y itself, and then we're also dividing -2s onto the term on the very end, so -1 over 2s squared. This negative sign's kind of bothering me here. I think we're going to distribute it in. So when you distribute that negative sign in, I'll also rearrange the order. So let's do 3 over s out front, and then minus s over 2 times the function y. All right, that looks a little bit nicer to me. Okay, now we can do integrating factor stuff. Integrating factor. Remember that in class, I think we called this sigma or little v. I don't remember exactly what we called it, but it's just that integrating factor. Sigma is coming to mind. I can't remember if that's what we called it too. But don't forget that this was e to the integral of p. And remember, our stuff is in terms of s, so e to the integral p of s, where p is the function coefficient on the y. So for us, it's going to be e to the integral of 3 over s minus s over 2 ds. This, just doing the antiderivative for, equals 3 over s is going to go to 3 natural log s, and then s over 2 is going to go to s squared. All right, we're going to use some powers of exponents here and split this e up. We're going to have e, I'll write it out, e to the 3 natural log s times, or sorry, not times, well, I guess it could be times e to the negative s squared. You could also move that e to the denominator as a positive s squared if you really wanted to. You know what? I think I did the antiderivative wrong. I think I'm crazy. Sorry. S over 2 does not go to s squared. It goes to s squared over 4. So this should be s squared over 4 here. I was going too quick. All right, and then the last little thing, remember we would bring the 3 into the exponent here. So it's natural log of s cubed. And then the e and the natural log cancel out. So our final integrating factor, I'll write like this. We have s cubed and then e to the negative s squared over 4. It's gross looking, but it'll work out. Okay. Now is the trick that we have for these linear differential equations. We're going to multiply both sides by this integrating factor, and then we're going to rewrite the left-hand side. So this is the linear differential equation trick. On the right-hand side, we're going to leave it as the derivative of the integrating factor. Not like that, though. Integrating factor. Great. And then times the thing that we're trying to solve for, and the thing that we're trying to solve for is our Laplace operator y. That's going to be equal to what was already on the right-hand side, -1 over s squared, -2s squared. And that's going to be times now the integrating factor s cubed e to the negative s squared over 4. Okay, now we want to integrate both sides. So the left-hand side is just going to stay the same, that the derivative is going to disappear. So s cubed e to the negative s squared over 4 times the integrating factor. My right-hand side, the s cubed and the s kind of simplify down a little bit. So we have a negative 1/2, we have an s, and then we have an e to the negative s squared over 4. I forgot to put my integral out in front. Integral of all this stuff. Yes. Okay, so now we just do this integral. We can take the negative 1/2 out. And then it's going to be a u substitution. So let me copy it down here. So we have negative 1/2 s e to the negative s squared over 4. I did the same thing I did last time. ds. And we're going to let u be that numerator there, the negative s squared over 4. So then du, the derivative of this, is going to be negative 1/2 s ds. That's kind of nice because that means that this negative 1/2 s is going to just substitute out. So this is what we have now. This is going to be equal to just the integral. Oh, it's not an integral. The integral e to the u du, which has antiderivative e to the u, and then plugging back in our u, this will be the antiderivative e to the negative s squared over 4. Plus c. Okay, so just to copy down what we have now, we have the left-hand side, which is the s cubed e to the negative s squared over 4. That's times the integrating factor, and that's going to be equal to e to the negative s squared over 4 plus c. Last step would just be to divide this whole term over to the right-hand side. So we end up with our Laplace operator is, when I divide this by the first term, the e's cancel, and we just end up with 1 over s cubed. When I divide it by the other thing, we're going to have the constant divided by the s cubed, and when you divide by this e, it's just going to come to the top with a positive exponent, so s squared over 4. Okay, there's some other little tricks that we can do here. So this, remember, is the Laplace operator. Remember that y of s is just that cursive L thing. So really what we have is that the Laplace operator of little y is all of this stuff here, just to copy it back down. One of the definitions that we haven't talked about for quite a while is, recall, the limit as s goes to infinity of this Laplace operator has to be 0. Okay, so again, I know this is kind of obscure, but it is something you're going to have to use moving forward, is that the limit of the Laplace operator always has to go to 0. If I come over here, the only way for this limit to go to 0 is if my constant is 0. So this says that c has to be equal to 0. Because if c is anything except for 0, this is going to blow up to infinity or negative infinity. It only can possibly go to 0 if my c value is 0. So thus, that says that my Laplace operator is just going to be the function 1 over s cubed. And 1 over s cubed is something that you can just look up. I'm looking this up in that table. We can find the inverse Laplace operator, and the inverse Laplace operator for 1 over s cubed is 1/2 t squared. And then that's it. So that is going to be our final answer. If I take 1/2 t squared and I plug that back into this differential equation, it will solve it. Not only that, it solves our initial conditions. Okay, that's it for this section, but there is one more thing I want to show you. So I'm going to pause it and bring up the book. All right, so just real quick, because I thought this question was fascinating. It's not hard. It's actually a pretty easy question. but it's a good application for using the Laplace operator. So we're not going to go through all the mathy, I just kind of want to read through it here. So determine the error E of t for the automatic pilot if the steering shaft is initially at rest in the 0 direction and the desired direction is given by G of t is AT, where A is constant. So this automatic pilot that it's talking about is the autopilot that planes use or boats use. It's basically a differential equation that tells the computer how much to turn the wheel to fix for small little errors in the direction that they're traveling. You can kind of see a little diagram of it here. So we have the desired direction, G, the error, which is where we're going, minus the desired direction. You plug that into this differential equation that tells the computer how much to turn the wheel to get back to the true direction. Then you plug it back into the system to see if there's another error. And if so, then you move the wheel a little bit, and it just kind of keeps looping like that forever and ever. Really cool. This just has us solving that differential equation to see how much we have to turn the wheel given a certain error. And it's the answers to is down here. So this E of t, this little error, is negative A over square root K divided by I sine of this stuff. So I know all of this, it doesn't really make too much sense, but the constants are all up top here. So based on the constants, the constant you can kind of think of as the force it takes, this K, to move the wheel. The A, remember, was given to us in the question. A is a part of the given direction that we're trying to go in. And then the I here, what was the capital I? The moment of inertia. Again, the moment of inertia has to do with how tough it is for the machine to turn the steering wheel. So based on all of this kind of stuff, we come up with a formula with how much force or how much torque the computer has to use to turn the wheel based on the error of how far off we are. So I thought that was pretty cool.